All right, so I think we have a full house. So it's a great pleasure to have Sabrina Pasterski with us today. Sabrina obtained her PhD at Harvard University in 2019, so we are very glad to have her back today. She's a high-energy theorist who joined the Perimeter faculty in 2021 after completing a postdoctoral fellowship at the Princeton Center for Theoretical Science. And research prior to joining Perimeter includes discovering infinite dimensional symmetry enhancements of the S matrix, a new observable memory effect in gravity, and a framework for generalizing these features of infrared physics to other theories. So please, take it away.
Okay, well, at least the first part of the talk is right there. So basically, very nice to be back, and also lovely to see all the familiar faces. Because this is a colloquium, or like I know the BHI is all interdisciplinary, I still have, like, the beginning will be like trying to just like set up a program that like Strominger and friends have been building up for a while now. And so that might hopefully be familiar to a lot of you guys. But then in the main kind of body of the talk is going to be about a paper with my lovely postdoc who happens to be in town today, in Gray Hugh. So you can talk to her about that too. Great. Okay, so celestial holography, just this lovely, cool program that lots of people have been a part of. My goal here is to talk about a particular kind of venture where we're trying to tie together this cool research program, which I'll set up in the first part of the talk, and other cool research programs within high energy theory. So let's just go back to the basics about why we're doing what we're doing. So our starting point is in some sense the holographic principle, which came out of the study of like black hole thermodynamics and Hawking's work. And so basically, if we wanted to try to see that quantum gravity should be holographic, there's many, like maybe a couple decades now, of interesting work following from Malpassini's conjecture that this ADS-CFT correspondence can really be realized from like top down from string theory. And so you have a notion of thinking that this quantum theory of gravity in some curved space-time is dual to or equivalent to some conformal field theory living on the boundary of the space-time. And this is an explicit realization of actually having the gravitational theory being coded in lower dimensional theory without gravity that you have from an explicit construction in ADS-CFT. But we want to basically think about how would we, if we didn't know what string theory is going to land on an explicit duality between ADS and some CFT on the boundary, you could instead work from the bottom up. And so this notion of starting from this, assuming that there will be a bulk and boundary duality, but starting from the symmetries and building up from there is something that you're able to generalize to more physically relevant spacetimes. And so the point of the celestial holography program is to find some duality for asymptotically flat spacetimes. And so by doing that, basically, we're going to start from the picture that's bottom up. And then hopefully our friends in mathematical physics and then eventually us too will have some explicit top-down constructions. And so that's kind of the goal. So now that I've motivated the ADS-CFT correspondence a little bit, and now the fact that I want to go to flat, that's what we'll start to do. So at the beginning of my PhD, I had the fortunate timing of being here in the Strominger group when there was a lot of cool stuff happening looking at just low energy limits of scattering. And so basically, this program that we're going to call celestial holography came out of attempts to try to understand how to apply the holographic principle to asymptotically flat spacetimes, focusing on this bottom-up approach where you want to match what the symmetries are in the bulk and the boundary. And so beautifully, each of these kind of aspects of the correspondence were studied a long time ago in the 60s. And so Bondi, Vandenberg, Metzner, and Sachs were trying to basically, I guess, find Poincare in some class of metrics that had zero cosmological constant but non-trivial matter, stress tensors, etc. And instead they found a much larger symmetry group. And kind of maybe in 2013, 2014 timeframe, there's a lot of fun excitement, understanding that those asymptotic symmetries were equivalent to Weinberg's soft theorem, also studied in the 60s, and certain memory effects that were studied at various times. So like the gravitational ones, I guess it's like 80s or so, 70s and 80s. And now there's more and more examples. So it's a very exciting time at Harvard, maybe 8 years ago or so, where basically there's this universal pattern of things coming from trying to start from the bottom up, start from symmetries of these asymptotically flat spacetimes, and see what you could get from that, what you could learn. And so roughly there, we had some fun kind of results already without talking about sociologaphy yet. And I put a spattering them on the board. So basically, at the time, the point was that there were an infinite number of symmetries. And I think Hawking came here and was visiting Harvard because of trying to impose those symmetries as constraints in scattering in the presence of a horizon. And then you can go into the questions of about confirmation paradox, questions of whether or not there's a firewall. There was also cool papers by like Riclario, Capitz, who's here, and Strominger. I really believe those are, like, it could be other authors too, and Pete, trying to reinterpret these IR divergences. And so that's nice because basically, okay, you could say, I only want to look at exclusive quantities. Can I define an S matrix that makes sense? And part of the reason why you would normally have this vanishing S matrix when you exponentiate these loop corrections is coming from the fact that you aren't obeying these conservation laws corresponding to symmetries. So there was something very nice there. Further, this framework led to more subleading soft theorems, and eventually, very recently, like this whole tower of symmetries in some sense is coming from at least collinear limits. And on this other side, we had a brand new memory effect, which is super fun because they might actually observe spin memory, I think in 5 years of like Cosmic Explorer. And the people here who do waveform stuff can tell me, or we can have fun talking about more like how the utility of that is actually something like more practically useful in the sense of trying to merge the analytic computations of waveforms onto the numerics for different windows of the spiral. So that's fun. And recently the work of Wald and others, I think, has been kind of reviving the story, talking about the consistency of having massless Hilbert space. Hilbert space for massive particles. So there's a lot of fun things that kind of came out of this just study of starting from the bottom up and the symmetries of aesthetically flat spacetimes. And the thing that I want to focus on is that all of this has a simpler description in terms of this theory living codimension too. So instead of the pictograph or whatever, here's the two things I want to say that we learned from that exercise. So first, the fact that flat spacetimes exhibit infinite dimensional symmetry enhancements, and that these should highly constrain scatterings. So that's going to be basically kind of the ethos of the celestial holography program. And the second thing is that these symmetries naturally organize into those of a codimension 2 theory living on a celestial sphere, and that's the word celestial in the story. So we're studying flat holography, and our starting point is that in the flat limit, there is this set of symmetries that maybe are surprising, and we want to see how far we can push them to tell us about this dual description that we want. Okay. So the celestial holography conjecture is this proposed duality between gravitational scattering and aesthetically flat spacetime and a CFT that's living on a celestial sphere. And so for most of what I'm going to talk about, I'm going to talk about massless theories and in 4D, then the 2D celestial sphere, but this should generalize on. Good. Okay, and so what I wanted to, for the subtitle of the talk, is talk about the extent to which this is also a collision of research programs. And so I think that, like, more practically, you could say that, like, literally the people working on celestial holography are coming from like crystallography, twisters, and amplitudes, and like quantum gravity, a la like what Luca should talk about later today, corner stuff. And then this whole soft theorem story that I just introduced. But if we try to just take a step back and see why it is that people who care about any of these kind of research disciplines should want to converge on this thing. So when I say celestial holography, I'm thinking like, look at the night sky. We believe in the holographic principle. How are we encoding whatever is happening in this bulk that we live in on that boundary? If you were an ADS CFTer, or something from Qubit, the people who do conformal bootstrap are studying what's basically happening on the boundary, often using the duality to kind of guide them. If from Qubit, people might be trying to talk about what's going on in the bulk or how the quantum information is encoded in different places. And then quarter people would be interested in two things, basically looking at some region of a space-time and trying to look at the symmetries associated to those causal diamonds. And that naturally carries over when I want to talk about the flat limit. So people studying flat holography before could be trying to basically take this picture, take the flat limit, and map that to S matrix elements. And so for us, we're basically looking at the flat limit starting here, starting from the symmetries of here, and basically now identifying being at the boundary with the on-shell momentum. So basically anybody who studies this for the purpose of going to the flat limit is essentially trying to go to the same goal. So you have this nice toy place where you have like gravity in a box. You want to open up the box And cool things happen when you open up, like hopefully not Pandora's box, but that's good. So maybe in words instead of pictures, you could say kind of the different mottos of the programs very crudely, mathematical structures that underlie the consistency of scatterings to a certain analyticity, like locality and whatnot, giving you consistent S matrix elements is kind of how the Amplitudes people are building up things. But if you understand that you can really take the flat limit, then not only people who are doing conformal bootstrap in this ADS CFT context should be able to map onto the S matrix too. And so they're just starting from conformal symmetry and the OPE to say something about the space of consistent CFT. And two different types of people coming in, like this quantum gravity perspective, the qubiters are looking at entanglement in space-time, versus the thing that was more directly correct connect to what we're doing is people like Laurent and I guess covariant phase space methods, where they're starting from the symmetries to build the Hilbert space. And while I won't have anything to say here, I know that there's a lot of excitement at Perimeter from the quantum gravity group about understanding how these two approaches are connected in their understanding of edge modes, and instead of looking at Hilbert spaces, looking at the operator algebras. So I know this is something super exciting going forward that I am glad to be around. So, yeah. Oh yes, of course.
Yeah, so on the previous slide,
Yeah.
can you interpret what you're saying to
Yeah.
the statement that if we understood sub-ADS locality, then we would understand holography?
I think that like Laurent would roughly try to say something like this. So I'm not saying, it's like, this is why I love being at Perimeter, because I feel like Perimeter is like, okay, we're like the BHI relative to this field, because we have a math is very fun. We have Laurent and quantum gravity, and then like quantum physics string. But we're also the only interesting thing in a 50-kilometer radius. So like everybody's there. But yeah, so I would say that the stuff, like, so he would be interested, instead of going to flat limit, he would be interested in bringing the corner inward. And so when you're doing that, I think it's less relevant whether like you're then extending it to like aesthetically flat space times or ADS. And so I think there's a strong reason to think that like that's a good link. And also like I think he's very enthusiastic about his understanding of what Ed's doing in terms of the edge modes that he's studied from these causal diamonds. So I would say
you what you think.
I think I believe him. That's what I think, because I don't know it well enough about, like, I'm about to hopefully get the Corner family to sponsor me, so that I need to know more about the Corner. Like, I think that, okay, so the reason why I think it, like, I only think about it from the point of view of the full causal diamond, because I don't know enough about the finite one. But I do know that a lot of the complaints kind of about, like, talking to Ed at IS, I would say, with this picture is, okay, you're matching in and out. And then also the extent to which we want to view like the Goldstone modes as canonically paired to these memory modes. And so something about whether or not we should really impose boundary conditions that like kind of kill one of the two. And like all these complaints about whether or not it's just a gauge symmetry kind of arise in the same spirit about imposing like Dirichlet boundary conditions, I think, on these finite causal diamonds. So that's the extent to which I believe it, because I know that part of the complaint there has been used to at least be skeptical of the program that I understand better at infinity. So that's where I believe, like, I have a bias to want to believe it, but then I also I love the fact that we can connect everything. So I'm going to help, but I don't look at these would help me there. So great.
Besides that corner stuff, I think there are also, I mean, there's one way
Yeah.
I think there's also like mathematical things that come up in this that are really identical.
Yeah, yeah.
To the sub-ADS locality.
Yeah.
Problem. Yeah, they look like the same. I mean,
I mean, then you could just kind of like try to extend like the little cost, like the.
It's the same problem from the other end.
Yeah, no, and that's why I think it's so beautiful. So like, I really wish I could say more about what I feel about it, because I feel like I don't feel enough about it. I just know that I see like these fields are colliding, and I'm like, okay, sorry, I'm gonna be a part of it, but I can't say more yet, because yeah, okay, good. So then let's go to the Celestial Dictionary. Okay, so I try to motivate that I really am excited, at least, if not, or like you should be excited, whether or not we know exactly why, because I think you could try to brand, you're studying scattering, or you're studying holography in a physically relevant, like, more astrophysically relevant spacetime, whether that's a finite causal diamond or like asymptotically flat to match the S matrix. Those are both very interesting questions. So like, I don't think anybody can question like that's something important to study, which I love. And then, so in this talk, I'll talk a little bit about merging things, but I think there's also some exciting directions for just like these papers out of Brussels studying flat limits of ADS-CFT and like seeing that the flat limit is different makes you realize that these system types of issues should be very important to really understanding what the flat hologram is. And yeah, okay, sorry, but that's an aside. So ignore what I just said right now. We can talk about that over this week. And what I want to focus on in this talk is just setting up a way to kind of a proposal to marry two highly developed yet somewhat disconnected fields, which will be this celestial holography story and the people who are doing conformal colliders. So like this is a rebranding exercise to some extent. Okay, so the first thing for the celestial dictionary, we're studying scatterings. We're going to prepare our initial and final states by pushing our Cauchy surface up towards the conformal boundary. We're interested in massive scattering, and so most of those Cauchy surfaces, to some extent, are hugging past and future null infinity. So this is a double Penrose diagram. I have past time like infinity, massive particles would enter here, massless excitations enter on the boundary. There's really an S2, but I've shown two parts, north and south pole. I go out to either spatial infinity if I look at the boundary of a space like a Cauchy slice, and time like infinity if I go up there. And so basically for massless scattering, I have data on this green and yellow diamonds. Good. So when I'm talking about celestial holography, basically, as long as I'm building up, and so this isn't what you want at the end, like the whole point of a top-down hologram is, you know, both sides of duality. And for instance, in ADS-CFT, you have the strong weak duality, so you can learn something about like strongly coupled condensed matter systems useful. But say I'm building up the dictionary starting from the book, then nobody should be able to complain about, say, for instance, well-defined celestial Bs, et cetera, because I know what I'm basically doing. I'm taking some correlation functions that would be the input for my LSE formalism. I'm restricting them to a codimension one null surface, which for the massless guys, I'm really thinking of it as being future null infinity or past null infinity. And then I'm just dimensionally reducing to, because the causal structure of that null surface is such that basically distance being x squared is 0 means you're at the same point in the celestial sphere, but could be separated any distance along the null direction. And so basically when we're building up these celestial operators, we're building up operators that if they were local in the celestial sphere, they could be extended along the null direction. And that's going to be kind of underlying why maybe the celestial description is a natural one. So this is what we're doing. And depending on which scattering basis you want to look at, you basically are integrating or smearing along the generators in different ways. So for example, you could just not smear it all, and you're looking at scattering in the position basis. And you know, this isn't like normally when you're talking about the S matrix elements, you're not Fourier transforming it back to an impact parameter. But if you do, this is where you start to really understand these subtleties about the phase space and like why they're like, you don't have square integrable news functions in some sense, because basically what's happening is, you know, for a given scattering process, what the tails are supposed to be at early and late U. And so that was underpinning our understanding not only of like the phase space that you need to be considering, but also the identification of asymptotic symmetries, understanding what memory effects you could do. And then also it's easier to just, I guess, start from the initial data on this Cauchy surface and then evolve into the book to talk about the relationship between bulk physics and boundary physics. There's a lot of utility to just taking your scattering amplitude and Fourier transform it. But this still leaves the question of when you're actually talking about phase space, why should you include, say, overleading gauge transformations? And so there's a time where there's this delicate balance between, okay, this is my phase space, these are the physical falloffs because I don't want to exclude some interesting process from happening. But depending on what falloffs I consider physical, I have to be careful about either dealing with the constraints that come from basically the canonical conjugates being unphysical, or I include them both in a certain way. And so there's really a delicate balance between what asymptotic symmetry group I have and what I'm saying about my phase space that I'm allowing. And so in the position space, there's all these like subletting soft theorems, and there begs the question, do I start adding like all these overleading large gauge transformations? I don't know. The nice thing about momentum space is you kind of know the structure of the amplitudes already. And so basically there you can start to use, like the whole point of this IR triangle in my story was that you could show that there were new asymptotic symmetries and new memory effects just from the soft behavior that you can compute in perturbation theory. So that's kind of nice. Basically, the whole point is, okay, so in position space, that's just a different basis transform compared to in momentum space, where I already am talking about the S matrix elements you're building up in Weinberg volume 1. So here the question that it doesn't quite answer is how subletting can we go? You really need to either know your theory, or be careful about what order limits you're taking in order to try to say that there's this tower of, say, symmetries in the Collinear limits. Okay, so what I want to say, the celestial dictionary and like the kind of the hardcore, or like the particular definition of what a celestial dictionary would be, is I'm in a boost basis. But I'd like to say that anybody studying these like flat holograms are still celestial people. So if you go into a boost basis, then literally by the kinematics, you have all of your operators in the boost basis. So this is the transform that's taking you to the boost basis. I could also write it in the position space as another slightly different integral kernel here. Two primaries of the Lorentz group. Yeah, exactly.
This seems like similar to, I guess, how when Penrose like studies like transformations on the light cone,
yeah,
like a certain light into celestial sphere.
Yeah.
So the boost basis like the boost to transformations that I guess map or mix points on the celestial sphere. And this is a basis, or is this basis corresponding to like the equivalent of boost would act on the celestial sphere?
So this celestial sphere is the same one in Penrose's story.
Yeah.
The fact, like, I guess a tool can, and I can try to debate whether the natural thing is like these integer bases from like certain constructions in twistor theory. But for me, so the sphere is the same. I'm not worried about any sort of twister construction or whatnot. I am just literally taking effectively like so if say I'm looking at the free wave equation, I'm looking at just a wave function in the bulk. If I know the data on that Cauchy surface, then I've specified that solution. And I'm just basically writing the data on that Cauchy surface in terms of a delta instead of an omega or a u. So I'm just trading out the energy scale for a continuous value of the conformal dimension, but the direction on the night sky happens to be the same as where the momentum is going to head towards because of this kind of accident of going to large R in a saddle point. I don't know if that quite answers your question, but the celestial sphere is the same.
I guess I was curious about, it's more of like, the question I was asking is the Lorentz group on the celestial sphere the same as the Lorentz group on the light cone? That's what I was asking.
Absolutely. Okay. So basically, you should think of it, sorry, I don't have the drawing or word maybe, but the way you want to think of it is basically if I do a boost, I preserve light cone of the origin and also light cone of spatial infinity, which is like kind of the opposite point on this Einstein cylinder if I'm looking at the Torres diagram. So yeah, you should be able to view it like when you look at the night sky, you look effectively the celestial sphere is the intersection of those two light cones. And so your little Millennium Falcon or Millennium Cessna Falcon, whatever, would see this kind of dilation of the points in the celestial sphere. And basically what I'm doing is diagonalizing the Riddler energy as opposed to the usual translation energy in the boost bases. So the fact that I'm doing this is just a basis transformation. And so this, if anything, this is where you're just changing the scattering basis. You're just okay. There's a little bit of angst from that, but okay, you can do this. The point is that you can't tell me that there isn't some 2D CFT because it's just kinematics. I can do this. So why would I do this? Okay, so why do we do this? We change our basis because when we're in this boost basis, it points out to us basically a whole tower of interesting currents that we can study. Okay, and so the main part of the stuff is going to evolve around basically two different derivations of these holographic symmetry algebras, which came out of the Harvard group. There's the one derivation, which is the holomorphic collinear limits derivation that I'm going to overview. And then there's the Laurent et al. Version, which is starting from the gravitational phase space. And they're complementary to each other in a way that I think is particularly like satisfying. And this route is going to land us directly on something that I can kind of compare more readily to this conformal collider literature. So that's why we're talking about it. But just to point out, there's basically a lot of other approaches to understanding these holographic symmetry algebras, and this is what's fun about having a large group of people with different backgrounds working on the same problem, like the BHI does, but the CHI, okay, and self-dual gravity, twisted holography, and people who are studying conformal self-films like Guevara, coming from Amplitudes. Okay, so now I'm going to review something that the Harvard group derived, so hopefully be kind. Okay, so first of all, we're going to talk about the getting the holographic symmetry algebras from the splitting functions and complexified collinear singularities of tree level amplitudes. Okay, so basically starting from, I think, like Guevara and then also Peyton Yan, working at the collinear splitting functions, and Himwich and Andy, of course, lots of names. I'm probably going to drop a couple of grad students in there. But basically, you're starting from the amplitude, you're starting from a tree level amplitude, you're taking particles collinear, you know, the tree level amplitude basically just has poles where they're propagators. And from the splitting function, you can extract what would be an OPE. And so from the point of view of this extrapolate dictionary, sure, if I take operators near each other on just on the celestial sphere, that's a collinear limit of scattering. So the fact that basically the collinear limits of the celestial story are related to collinear limits both in the bulk space-time operators approaching each other in the conformal boundary, or collinear limits of scattering amplitudes just comes from this dimensional reduction of null infinity. But makes sense if I really did have a 2D CFT, and I'm going to say, let's say I really do have a 2D CFT, then if I take two operators close, that's encoded in the collinear limits of the X matrix element that I'm transforming to get to it. So I'm applying that integral transform here. And then I get this collinear limits as a function of the weights. Beautifully enough, if I then look at where those gamma functions have poles, I can extract the collinear limits of the residues. And so just to keep in mind, these holomorphic collinear singularities, it's not so much a soft limit as it is like the leading collinear singularities. So it comes from when I get the propagator attaching to another external leg. And then the thing to keep in mind when I'm writing down this tower of integer weights is that roughly I'm at either spin plus or minus 2. And depending on the value of the weight that I go to, I am going to have, on the next slide, an interesting structure of the conformal multiplets. So basically what's happening in the boost spaces that's maybe interesting is, okay, so I know I have the Lorentz group. I don't necessarily have the same inner products as I would in a normal 2D CFT, but one can try to find ways to make my Hilbert space like in and out inner product, basically like map that to the 2D radial quantized one. But if I just start from my boost spaces, because of the nature of the fact that I really didn't have a 2D theory, I had a 2D theory with this extra null direction that I want to get rid of. I had the power to tune my weight in some sense. So it's almost like you can always have, like if you have a question of, okay, say I have a CFT, I want to look for null states, then like there's some, you'd have to basically happen to have the right spectrum for these like null states to exist, versus I can choose my value of delta such that I'm in a multiplet that has a primary descendant. And so I have this whole tower of soft modes here that will all basically have some primary descendants. And if you go high enough, you also have like left and right primary descendants. What I'm going to do now is I have normally a principal continuous series of weights. I have a continuous set of weights because I have continuous coordinate u. And I do the Mellon transform with a certain real part of the dimension just so that the integral converges. But then I analytically continue that dimension, I would have a set of poles, basically this tower of integer values of the weight that go more and more negative. And those conformal dimensions have primary descendants from the point of view of the SL2C, Lorentz group representation theory. And so I could posit that some one of those two sets of descendants, say like in this case, the Z bar descendants, actually truncate at that primary descendant, like I would expect from like the notion of like the right hermiticity conditions on like going from into out state in a 2D CFT for radial quantization would actually guarantee for me that those states would be null. So say I assume that truncation, it definitely works within MHV amplitudes. And then I'm basically just manipulating those collinear limits of scattering for the full residue here. And they showed in this beautiful paper, like the one with Alfredo and then also Andy, Kimmich, Alfredo, Monica Pate, who was a BHI fellow, and then Strominger, showed that they had this cool loop register, or like wedge of the loop of like W1 plus infinity algebra coming from these collinear gravitons, so same helicity collinear gravitons. And the cute thing there is they're really using, I would say, treating it like it is a 2D CFT, using basically some complexified version of a radial ordered commutator and assuming that the primary descendants decouple. So it's cool that basically you're able to get this kind of interesting, very, very rich symmetry structure compared to the whole story that started out was basically the infinite number of symmetries that you've got in the flat limit wasn't an infinity in this case, it was an infinity in the case of, okay, say I have a charge and I accelerate it. Its electric field is going to basically now be kind of pancaked if it's moving at a faster velocity. So there's some angle dependence. And I could try to build up an arbitrary angle dependence to the Coulomb field just by having charges that have been moving forever in different directions with different speeds. But that's just an angle dependent charge. So it's basically like a function of the two sphere. This now is basically going every order in R in some sense, or every subleading order in omega. It gives me more symmetries. So it's like another infinity of symmetries. And so you have so many symmetries, like, wow, okay. Very cool. Now, hopefully, I think some people here might try to debate about whether there's this part, but basically, I would say the cool thing about part of that derivation is that it piqued the interest of a lot of people who knew twist series and just holography. And so the people who come from Penrose's school immediately recognize this as like the nonlinear graviton constructions, like giving you these symmetries of self-dual gravity. And I would say that for the haters are going to hate, one of the complaints you always get when you talk about these cool symmetry algebras, okay, well, like, oh, you're at tree level, like, how does it extend? And you either have to be very confident that, like, the point is that the dual theory really does have these symmetries, and you're going to start from that, which had some beautiful implications, like doing the same thing with like the black hole here story. Or you could say, okay, I hear you a little bit. Let's see if there's another way to derive it. And this is where it was really beautiful work by Friedel, Colloquium, and Franzanetti, where they are able to get the exact same symmetry algebra. Instead of using this kind of 2D CFT constructions, they're just sticking to your usual radiative phase space and looking at the Poisson brackets. And so as a summary of what they did, they basically set up a recursion relation to get them these sets of dimension 3 operators defined in terms of C and C bar, and basically higher and higher numbers of those guys that obey under just the A and A direct commutation relations, the exact algebra that you wanted. So in this case, there's not this restriction to the wedge, but they're able to reproduce the thing underlying this delta W infinity here. So what I want to point out is that there's another statement in that paper, which is that basically for them, they're really interested in the fact that these recursion relations look like equations of motion for them. And the reason why it's a little bit more subtle. So basically for them, you can say that I have these higher and higher u moments. So I integrate the news, and then I integrate u times the news, and I integrate u squared times news, et cetera, et cetera. And then I add in higher particle terms so that the algebra is what I want. They then can recognize that some of those guys under the equations of motion match to like the bonding mass, the angular momentum aspect, and deeper kind of terms in the Weil tensor near spatial infinity. And so the equations of motion basically relate these kind of moments of the shear along scribe to terms that are at spatial infinity. And so they go deeper than the bonding mass angular momentum aspect, but in this whole story of like charge conservation and symmetries of the S matrix, the point there was that you have this antipodal matching. You're able to match data of the metric near spatial infinity coming from the past of future null infinity and the future of past null infinity. And so the equations of motion play the role of giving you an object that you can antipodally match. Without the equations of motion, you're basically constructing a representation of the symmetry algebras you get from the holomorphic collinears, limits of scattering on the radiative phase space. So basically just some sets of free oscillators with given spins. So the next part of my talk is going to basically be saying, okay, for the BMS subalgebra, which is the one where we have all this, the first start of the soft symmetry word identity story, you're able to realize basically that the thing, that recursion relation you can stop for like the lowest values of spin, just a linear term and a quadratic term. And then you have the splitting between a soft and a hard piece. And similarly, splitting in the hard piece between a gravitational part and a matter part. So for example, the leading soft graviton couples say to the anic operator, and this would be the anic matter term, and then the shear inclusive anic is roughly. So the kind of premise of this paper with Ian Gray is like, let's take exactly that same construction and add matter to this full tower. So now basically, the thing that I just want to point out is this kind of gravitational matter splitting that we a little bit take for granted. And so now I'm going to actually write these specific down, which would have been maybe helpful a couple slides ago. So basically, if you want to realize the graviton matter kind of OPE, like the holomorphic collinear singularity story, and the algebra that comes out of it from the radiative phase space, you're going to try to add matter terms. The linear part is going to be the same. I'm going to still say that these u moments of the shear are, in this case, I'm using the opposite holistic guy just for simplicity of matching to Laurent's paper, are these single particle terms. And then you want the two particle term to basically be such that the commutation relation of the two particle term with the matter field matches the OP, the coupling of the matter field to the graviton, right? And so that can actually set for you the coefficients. So basically here, all I'm doing is I'm matching the thing coming from the external matter field coming out, graviton vertex, and saying I want to reproduce that holomorphic collinear singularity from the phase-space bracket. So you need a term that's quadratic in the matter field so that with the matter field is another matter field. And so one can reverse engineer these quadratic terms, or similarly for the graviton case, just solve the recursion that Laurent had. But for the matter case, sorry, so for the gravity case, you can solve his recursion. For the matter case, I want to match the soft theorem. So I get a quadratic term. And then I can try to go particle number by particle number and go to 3-particle term. What do I need to add to make it so that the algebra closes up to quadratic order? And so the quadratic terms and quadratic terms give you another quadratic term. The linear term and the cubic term also give a quadratic term. And to make this algebra close, you have to engineer a cubic term. So it's kind of cute. Is that basically, so I'm kind of saying, screw this recursion relation. I'm just going to try to go up to the S equals 2 generator that would give the rest of the W infinity algebra. Know that the linear term has to be the more and more subleading soft gravitons to match the fact that the thing you've inserted in the S matrix element is this like integer weight, negative integer weight graviton. And then the quadratic pieces match the algebra corresponding to the actual soft theorem, the coefficient of that soft theorem. And then the cubic term is there to make it close up to quadratic order. And then you could imagine going further and further particle number. And so basically what's kind of cute is that what happens is that when you go beyond the BMS subalgebra, basically the matter term needs a graviton term in order to cancel. So you don't have this nice structure of just like the soft and the hard charge, where the hard charge only has matter and the soft charge is a linear and graviton. The hard charge can have like a quadratic graviton piece coming from like the total energy lost by like the gravitational radiation and a matter piece. For the more and more subleading or higher S charges, you have terms which are like gravitons coupled to the matter fields. And so, okay, maybe this is not surprising because these objects are basically the same type of ones that you would have. If you got rid of the graviton, you'd be looking at some sort of matter theory, and you'd be looking at the operator algebra of these light ray supported operators in that matter theory. That matter theory is a theory kind of living near null infinity. You might think that if it's basically asymptotically free, to what extent it's approximated by the free 40 CFT. Basically, you would have thought that maybe Cordova and Xiao and others who are studying these light ray operator algebras and CFTs would have found something more. So this transitions me to the main part of the talk. So how, oh my God, okay. Like you guys can always leave, but I'm gonna keep. Sorry, but this is the fun part for me. So basically, okay, you have these cool people starting from 2008, Hoffman Lucena, and it really actually dates back a lot further. So you don't know how many years of like being a grad student and people will be like, well, what have you done that's, or like, what's this used for? These Anik operators, correlation functions of them that are this hard charges in our story, were used even in precision tested QCD, which is kind of surprising to me. Like I didn't realize like going back in the day, like they were using that to actually test that. So conformal collider physics is trying to normally use like insights from radius CFT to compute observables in this CFT that are supposed to be relevant to particle experiments. And so they're literally looking at something that's produced from a scattering process. They prepare a slightly different state, but they have these operators at null infinity, just like we would for preparing our state. So the cool thing is this program has a lot of like, nobody doubts like well, what have you learned from these programs? Okay, you've bounded some anomaly coefficients. You've identified good observables when you're looking at, say, these detector operators and like near Wilson-Fisher fixed point. You've said something about modular Hamiltonians. There's a lot of cool applications that have come from like the same objects, and that's what I'm basically trying to. So these light ray operator algebras, one of the first kind of nice intersections of this Strominger et al. Group and this story coming from Hoffman-Lucena was this result by Cordova and Xiao in 2018, where they basically looked at just unitary 4D or in any case NED CFTs and operated to a light sheet and try to see if they could generally show that those matter stress tensor moments basically obeyed the BMS algebra, and they did. So roughly speaking, they just have a unitary 4D CFT and operators on a light sheet give you BMS. So that would make sense in the story before, where we have Q soft and Q hard. If you really have a factorized Hilbert space where the soft part and the hard part come back separately, then the soft part and the hard part should both obey the same algebra, and they're just giving me the matter sector there. And so what's kind of cute is, from the celestial holography perspective, basically all of these other generalizations of the Anik operator are also celestial primaries. So they have definite weights. And So basically, if anybody says, "Oh, why are you looking at a boost basis?" Like they're looking at a boost basis too. They just don't care. Yeah, this is like it's kind of cute when you talk to them. They're like, "Why are you looking at a boost basis?" And it's a very like just because it's a generalization of the ANIC. But in practice, the reason I guess is not so surprising that okay. So when you have a primary that's at spatial infinity, that conformal frame is such that like the action of like say being a primary, so K annihilates the operator at the origin, is that translations annihilate the operator at spatial infinity. So any primary that's sitting at I0, whether or not it's a light transform so it's actually extended along sky, those guys are going to be annihilated by translation. So there's zero energy. And then the only thing left over, if you're looking at the Poincare subgroup that preserves the conformal boundary, is going to be Lorentz. So maybe that's why they land on these boost eigenstates. And they even land on like shadow transforms like we have. And then the other thing is that if you're looking at the zero energy sector, that should be somehow closed. And so that's why they're kind of starting from ANIC and these generalizations that are also zero energy, et cetera. So there's a kind of reason, reverse engineered reason for why they look the same thing.
That's a question.
We should keep it
Okay.
at the end, yeah.
Okay. So basically, there's a hell of a lot of cool, really, really cool people who are looking at the same operators as us. But the reason why we really never encounter them so much is because these guys are like the quadratic terms that would appear like higher multiparticle states in the celestial OPEs. And the reason why they wouldn't care about ours is because they're only looking at one value of the conformal dimension, which should annihilate the vacuum. So it's kind of like this, not Romeo and Juliet, it's like basically the tragedy in the sense that like these objects are almost zero for our out states. And so we're the contact terms, and so we set them to zero. And our first objects are zero in their context because they're either not looking at gravity or they're looking at only one value of the conformal dimension for which it is zero. So it's just like, that's why there's been a disconnect. But basically, the Symmetry operators that are featured in the conformal collider literature are celestial primaries, the corresponding 40 CFT correlators, probably the conformally soft matter sector of the 2D celestial CFT. That's just true based on kinematics. And in particular, you can go back to whether it's Bellin's papers or Melisena, other people's different definitions of things. And these matter charges that appear in the celestial story are contain the same term. So roughly speaking, these higher and higher U moments of the stress tensor are appearing in this W infinity story. And so on the one hand, you can just say, okay, well, all of the story of like what Laurent is building up are extensions of this notion of these detector operators or conformal collider operators. But in practice, the way it's interesting is it's kind of twofold. So you're studying the same operators in different states. Normally they're looking at inclusive processes. So they wanted like IR finite observables, and it ties into our story because we're looking at, like say there's this like features of the soft factorization coming from the asymptotic symmetries. So they're not unrelated there. But they're looking at the same correlation functions, just basically time folding back. And if we want to really consider scattering, we don't want to restrict ourselves to basically some finite number of particles well separated. So the ANIC is like zero away from those insertions. We would also want to be carrying with the same states. And so these approaches are quite complementary. So basically, anybody who gives a shit about not computing loop level computations, like, I mean, obviously sometimes we have, but basically that community is starting from like higher loop order than normally we have. So we can just take their results and say, yes. Similarly, and honestly, curiously enough, they actually run into issues with, like there's so many states with definite, say, boost and spin, like including these like shadows and whatnot, that they don't really know like how they're supposed to, like they don't understand why there's this funny mixing that they've seen, like this detector operator paper. So I would hope that because we have a good combination of operators coming from these celestial symmetries, we might be able to give them a reason for why some of their like beyond BMS organized the way that they do or not in these detector operator stories of like some stuff and smoke and hope. So, and in both stories, the question of whether these operators even exist is important because you could be worried like, okay, so just looking from the oscillator algebra, you should have in this Bellin story, basically these U moments of the stress tensor should be a Witt algebra. But if you look at it in actual correlation function, something breaks down. And for us, we care about these operators being well defined because that's related to this question of whether or not we can really talk about the integer weight basis as being a complete basis in some sense in our celestial story. So those are very tied together. And I wanted to point out, so like the point of this talk was to make a very concrete contact with something coming from a very different and independently developed subfield where we're studying the same objects. And want to emphasize that really, even if anybody gives you shit that you're just looking at kinematics, like symmetries are really, really powerful. And a lot of people are looking at the same kinematics. And so this is basically ripe for the picking as far as basically celestial taking over. And so going back to Symmetry, we have things coming from these Ickham and Qubit, often in Melisena, intrinsically bootstrap, these complex spin light ray operators, and amplitudes like these soft limits of scattering, all colliding to celestial geography. And that is my talk.